very happy to see a few faces. I was hoping to see a few more, but I hope eventually people will come along. So today we will talk about not so much about my research, but I'd just like to tell you about what is going on in astronomy. And I'm very happy to tell you that new astronomy is kind of on us. We are just starting a new wave of astronomy, and astronomy, as you know, is a way of looking at the universe and trying to figure out, how the universe works, right? So how planets move, how stars shine. Nowadays, a lot of transients. When you look at the sky and wait for some time, you see weird things going off, popping off at random times and so on. Try to make sense of all kind of things. So usually, these kind of observations are made in electromagnetic telescopes, right? Telescopes that you know of. How many of you have seen a telescope? All of you have actually used a telescope. Oh. So you have telescopes of all kinds. Telescopes that can observe in normal, light, infrared, ultraviolet, X-ray, all sorts of telescopes. We even have radio telescopes and so on. So that's the standard way of doing astronomy. And what I'd like to tell you today is a new type of astronomy using a new probe. So this is not electromagnetic light that we are trying to receive from astrophysical objects. This is something else. I'd like to tell you what it is, first of all, how we detect them. There are a lot of technology that goes in, a lot of mechanical engineers. It's not just physicists. I mean, a lot of mechanical engineers, a lot of electrical engineers, a lot of signal processing goes into the detection of these extremely faint signals. And finally, I'd like to tell you what we can do with it. For instance, can you measure how old the universe is? Can you tell how big it is, or how fast we are accelerating and things like that? Can you tell something about dark energy, expansion? So you'll see that these guys are very useful in that respect. Okay? So let's get started on this journey. So as I was saying, can you please switch this? Ye lights off kar di. So the dawn of astronomy is, of course, electromagnetic astronomy, and that involves only visible light. And this was the only form of astronomy until about 1930s. So from whenever we started looking, the earliest telescopes were our own eyes. We just stared at the sky, tried to make patterns. Human beings are very good at making patterns. So we made a lot of patterns, right? For instance, all these patterns of stars. Rashi, like Virgo, Sagittarius, and it's very amusing what the human mind will do when you have nothing better to do. Now, of course, you have other things, other forms of distraction. But at that time, you looked at the sky, you had an early dinner, hopefully, and I hope it will go away. Yeah, okay, good. So, and this light that we were observing until 1930s is the light which is basically coming from ordinary stars. For instance, a very nice. Does anybody recognize what this constellation is? So, and of course, you watched planets, as many as you could. And you could sometimes, because there was hardly any light pollution until 1930s, you could also observe some galaxies. Right? So, and the picture that you get is a very serene view of stars, planets, and galaxies. Right? If I look at this spectrum of electromagnetic radiation, for instance, these are very short wavelengths and these are very long wavelengths. All this observation was made somewhere here, like in the visible band, something that you could look up just by your eye alone. And then after 1930s, lag. So, in fact, we have been doing electromagnetic astronomy in this band for a very long time. For instance, this is the deepest view of the universe using the Hubble telescope. And you see, the same kind of picture is kind of reinforced in your mind that, it's a very serene picture of galaxies of various kinds. And one of the things that you can look at is you can break it up into different distances and then figure out how the galaxies have been evolving. So this kind of gives you a picture of how structures got formed in the universe. And looking up at this night sky is actually quite a good idea. For instance, there was a person called Olber who looked up at the night sky and actually argued, why should the night sky be dark? Has anybody heard about this Olber's paradox? Olber, O-L-B-E-R. Olber actually looked up at the night sky and he kind of made a very, very simple calculation and showed that, look, if the universe is infinite, as was the cosmology at that time, that was the understanding of the universe. He argued that the universe, the night sky, if the universe is infinitely large, the night sky should be as bright as the day. Okay? But the night sky is not as bright as the day. In fact, it is dark. So that this apparent dichotomy goes by the name of Olber's paradox. And not only philosophical questions, but also physics questions can be answered by just staring at the night sky. So it is not such a bad idea. This is like 1950s, like you to press a button and then wait for a few seconds for things to come up. Now, in fact, one of the consequences of Olber's paradox is that the universe, just by looking at the night sky and arguing that it must have been, if the universe was infinitely large and existed forever, the night sky would have been infinitely bright, but it is not. And hence, one of the conclusions of that argument was that the universe must have had a beginning, which we now know as the Big Bang. So, yeah. Sorry? Yeah, so I invite you to look at Wikipedia for a small calculation, which you can do with +2 mathematics. Okay? You'll be convinced that the universe will be infinitely bright. It's not very difficult at all. I don't have the resources to write down an equation right down, but I promise you that it is a 2-line calculation. So now, as I said, Olber concluded that therefore the universe must be finite and should have had a beginning. So the question is, where is that light? If there was an explosion in the beginning, where is that light? And of course, for a very long time, there was no evidence for that light, but until we started looking at the universe at very long wavelengths. So when we started looking at the universe in microwaves and radio waves, we found that no matter which direction in the universe you look, so this is a projection of the universe on a 2-dimensional surface. So therefore, it has this weird shape. So these are projections of a sphere. But you see that you can see certain hot spots and certain cold spots. But no matter which direction you look, you see that there is this heat, residual heat. So as the universe expanded, basically what happened that this light, which was emitted at the beginning of time, that got stretched till microwave, until they became microwave radiation. And you can, and this was accidentally discovered. In fact, people thought it was pigeon droppings. We always think it's pigeon droppings, right? So what they did was they put up a microwave antenna, and no matter which direction they steered this antenna, they always found that this kind of salt and pepper kind of noise. And of course, I don't know how many of you have seen an old TV from 80s and 90s. If you switch on the TV, you see the salt and pepper noise. That's basically Big Bang radiation coming to you. Right? So that is, of course, some of it is electronic noise, but basically it is it's a signal from Big Bang, which you were actually seeing in 1990s on your old TV sets. So the message of this picture is that once you move your horizon from being just seeing visible light to seeing the universe in a different wavelength, you immediately start seeing that the universe is not as serene as you thought it was. It's actually quite a violent place. You'll see more violence in a minute. So it is here on my screen, but okay. It's so wild. So later on in the century, last century, we had radio telescopes. So for instance, here is an array of radio telescopes. Turns out that a single radio dish sometimes is not the best way to resolve objects in the sky. So you need an array of them. And you kind of synthesize the image by combining the time delay across various combinations of these radio telescopes. It's a very fantastic subject of how to synthesize images from these radio telescopes. India has probably one of the largest radio telescopes in the world. Do you know that? You know which one it is? Where is it? It's a place near Pune, right? It has I don't know how many dishes, but it's shaped in the as a Y configuration. So when you see the universe using radio telescope, something very interesting happens. So this is what you see in a radio telescope. So this is the radio galaxy. It's called NGC 383. And you see that something phenomenal is going on over here. So there is this is called an active galactic nuclei. So it's basically a black hole that is sucking up accreting matter. But not only, of course, that of course emits a lot of radiation because the gas gets heated up, right? And there is this inverse Compton effect because of which X-rays start emitting. But apart from that, you see there are these plumes of gas that are being thrown outwards. I mean, this is huge. It's the expanse of this is bigger than the galaxies. So huge. So very, very violent processes are going on, which you did not see when you were seeing things in just the electromagnetic spectrum. When you looked at the universe in X-ray, you see that this, I mean, of course, there is this central object that is very bright. These are called quasars, by the way. Have you heard this word before? Quasars? So these are quasars, and this quasar is an object which, of course, definitely involves a black hole, which is sucking up gas. It's very hot, but then, there are these plumes of gases. These are called jets. These jets, nobody really understands. This is, I mean, I hope one of you can, will eventually figure out what this, solution to this problem is. But nobody really understands how these jets are thrown out. I mean, this is an unsolved problem in magnetohydrodynamics. I mean, but nevertheless, that's what you see. So very, very violent events when you see the universe in different wavelengths. Of course, now you have the James Webb Space Telescope, which was recently launched. Yes. Yeah, that's right. So nobody knows. The answer to that question is it's an unsolved mystery. Of course, we do have some idea. So, it's like, so if you pinch gas in one direction, so it creates certain aerodynamics because of which gas is emitted. But what is the precise mechanism of that is not. People are trying to simulate it on a computer using whatever physics we know about very, very, extreme. So this is all, everything is extreme near the black hole, right? Gravity is extreme, pressures are extreme, velocities are extreme, everything is extreme. So physics at the extreme we don't have a laboratory for such physics, right? So that's why we do astrophysics. We go to astrophysics to understand matter at the very extremes. And we will talk about that. Gravitational wave is one such scenario, as we have extremes of things. So the answer to your question is nobody really knows. So I hope you will find out. You never know. So James Webb Space Telescope is another such space telescope where we are going in the infrared, so not visible light again. So, and the reason why you want to go to infrared is because you want to look at what is happening at the center of galaxies. In the center of galaxies, of course, there is a big black hole sitting over there, but it is surrounded by dust because of stuff that is falling into it. And in order to see that this dust, what it does is that whatever light is trying to come out, it tries to redden it. That means it redshifts it to reddish light. Therefore, infrared telescopes are best suited for looking at things that are very far away. India too has AstroSat mission, which is a collection of several sensors, usually working in the X-ray and the gamma ray spectrum. Okay? So the advantage of such a thing, such a telescope, is that usually you want to look at transients, things that happen over time scales of a few minutes or a few hours and things like that. And there is no time to first look at it. Different kind of physics emit radiation at different wavelengths. So you want to see all of that happen at the same time. So therefore, you have this whole array of different sensors which look at the same object in the sky at different wavelengths and try to kind of do the inverse problem and figure out what is going on over there. So the upshot of this whole pictures, showing you all these pictures, is the following. So basically, observing the universe in new wavelengths of light has always led to massive revolutions in astronomy. So we have always seen new things which we never even imagined in our wildest dreams. So, and such a new revolution has now occurred. We are now able to see the universe in a completely different way, and that is through gravitational waves. So the question naturally arises, what might we expect when we observe an entirely new spectrum? What is it that you want to see? I mean, what do you expect to see? In order to do that, let me jog your memory and tell you that there is a slight problem with Newtonian gravity, because I need to really tell you what gravitational waves are. And this is what all of you must have studied in +2, right? This is Newtonian gravity in one equation, right? You might have seen this form, this is a form that you might have seen or probably remember, which is if you have two masses m1 and m2, they attract each other through a force, which is a gravitational force. And this force is inversely proportional to the square of the distance between them. The m1 attracts m2 exactly the same, with the same magnitude as m2 attracts as the other way. Right? But basically, you can describe, rather than these forces, sometimes physicists prefer to describe situations with potential. So these are conservative forces, so you describe these things in terms of potential. And this is an equation which describes how the potential is distributed if I give you some matter distribution. So on the right-hand side is matter distribution. This chair, this speaker, these chairs, you, me, everybody. And then how does the potential of this distribution of matter, how is this described by this equation? And of course, we all have been taught enormous number of ways to solve this Poisson equation. Have you been taught how to solve a Poisson equation? Have you seen a Poisson equation? Laplace equation? You have seen, right? So you know how to solve for this equation. So basically, this equation describes the gravitational interaction between two bodies, and of course, when you have two masses, they are equal and opposite forces, and it is very successful theory. So the interaction is described by a force according to Newton. So Newton describes gravity as a force between bodies. And it is a very, very successful theory. In fact, it is applicable to a wide range of problems. And it is so successful that even if you forget Einstein, you will be able to go about your daily business in life with absolutely no problem, right? So you are able, we launch spacecraft based on this equation. So we are actually putting in billions of dollars trusting this equation to reach Mars. There is no Einstein over there, just Mr. Newton is telling us how to move. So the gravitational potential, this phi, obeys the Poisson equation, but there is a slight problem. The problem is that there is no time over here. As in, suppose Vineet gets a call and he has to go somewhere. So obviously the mass distribution on the right hand side has changed, will change, right? So somebody in the moon should be able to now get an updated phi. It makes sense, right? If you change the right hand side, the left hand side will change. Right hand side is the distribution of masses. So suppose Vineet leaves the room. So the right hand side changes, but so I expect the left hand side to also change. Now look at this equation. The left hand side, this equation, there is no time built into it at all. This operator, del square operator, is a purely spatial operator. So what does it mean? It means that as soon as Vineet leaves, somebody at the edge of the universe would know that Vineet has left instantaneously. There is no delay. This information travels instantaneously. That is not allowed. No information can propagate instantaneously in this universe because it violates a very, very successful theory that we have, which is called special relativity, Einstein's special relativity, which tells that information cannot move faster than the speed of light. The fastest object in this universe is the speed of light. So somebody at the edge of the universe, till now, suppose everything was static and it knows what the potential of this room is somewhere very far away, should not know instantaneously that this mass configuration and hence the potential has changed. So Newtonian gravity, while it's a very successful theory of gravity, has a little problem in that it is not consistent with special relativity. Now enter Mr. Einstein. And Einstein's prescription for gravity, see, as physicists or as scientists, we only can build models of trying to explain what we see in nature. Right? So Einstein's picture of gravity is that there are no forces. Unlike Newton's idea of gravity, which is actually two masses are interacting through a force, Einstein has a geometric theory of gravity where mass creates curvature in space-time, and the curvature dictates how masses move. Now, since there are no forces, so therefore, if you have a freely falling mass, it has to fall in a straight line. There is no other way for it to fall. There are no forces. So then, how does this dynamics of mass affect these things? So whenever there is a dynamics of mass, for instance, if I move my hand, right, there is some dynamics that is involved. It leads to a change in curvature that propagates out in the form of a wave. So if you think very crudely, it is like saying that the change in this potential, that information travels out as a wave whose velocity is exactly equal to the velocity of light. So this is what we are calling the gravitational wave. Of course, at slow speeds or for very small masses, Einstein's geometric theory of gravity gives exactly the same answers as Newton's theory. So there is absolutely no problem. So you can think of Newton's prescription of these two bodies interacting through their masses as an effective low energy theory of Einstein's geometric theory. Okay? And now you might think that, oh, this is, asking for too much, but you will find that general relativity, so this geometric theory of Einstein, it is also goes by this name of general relativity. And it is actually closer than you think. For instance, all of you have a smartphone, and since none of you know Gandhinagar very well, you might want to go outside the campus relying on your GPS navigator. You might use Google Maps or something like that. And Google Maps actually uses a technology which is called GPS navigation. And GPS navigation requires a precise timing information. So these GPS satellites are actually very far away from the Earth. So the gravitation over there, the gravitational field there, and this person who is holding up a phone, they are different. So when the signal comes from this point to this point, you have to factor in this difference in gravitational potential using general relativity. And if you didn't do that, your GPS navigation will be off by several kilometers. Okay? So general relativity is actually in all your pockets, in your smartphones, basically. So general relativity has also passed several observational tests. For instance, people have been looking at Mercury. Mercury is a very strange fellow. Mercury is the planet. I mean, it's a very, very strange fellow. We'll come to it. People have been watching Mercury, and then Mercury does some weird things. Does anybody know about perihelion advance of Mercury? Okay, good. I will tell you. And then the other thing that I want to talk about is this deflection of light from distant galaxies, both of which have been measured, and both of which cannot be explained by Newtonian gravity. Newtonian gravity is very, very precise. So suppose you don't want to worry about the 11th place of decimal. You don't want to make very precise measurements. That's fine. You can live with Newtonian gravity. But if you start worrying about observations, which, very, very fine, super fine observations, then Newtonian gravity cannot explain certain weirdness that you observe in the universe. And then you have to bring in general relativity, which has passed several observational tests. Let me tell you a little bit about the first one. Look at this fellow. This is Sun. And we are talking about Mercury, which is this blue dot over here. Mercury is very hot, by the way. And it's going around the Sun. And if you had just Newtonian gravity, Mercury would happily do this elliptical orbit around the Sun, as all planets do. But the problem is that our ancestors had a lot of time on their hands. So they were observing Mercury for a very long time. They said that, hey, there's something weird about this planet, because what it does is, so the closest path, the closest point of Mercury to the Sun is called perihelion. Okay? I don't know why it's called perihelion, just called perihelion. And they observed that this perihelion is not fixed. The perihelion starts moving. What it means is that this Mercury orbit starts moving around like a flower, the petals of a flower. It precesses. How much is this precession? You'll start laughing. It is 43 arc seconds in a century. Can you imagine how much time these guys had? 43 arc seconds in a century. If I were you, I'm this person doing my lab in some IIT, I would say that, just fudge it. Forget about it. Okay? But these guys did not fudge it. It was there. And there is nothing in Newton's gravity which will tell you that this is supposed to happen. Of course, now, you bring in theories. If you bring in 10 theories, they will give you 10 theories. And that is their job. So they said that, look, Sun is not the only one which is affecting the Mercury gravitational. There are other big planets, right? Jupiter is there, Earth is there. So let us fold in all those effects. When you fold in all those effects, you do start seeing something like that. You do start seeing that Mercury's perihelion starts advancing a little bit. But it doesn't explain all the observation data fully. There is a little bit that is left. And whatever was left was found to be a pure gravitational effect, due to which was explained by Einstein's theory. And this is how much it is: 0.012 degrees in a century. It's a tiny effect. So that's again, I'm saying, don't throw Newton away yet. Okay, Newton explains everything apart from this little thing, 0.012 degrees in a century. If you're willing not to be bothered by this little difference, then you can happily live with you. But that's not how the universe works. That's what I'm trying to say. Let's look at another fantastic observation, which only can be explained by general relativity. So here is Earth, and you have a telescope over here, and you are looking at a very distant quasar. Quasars are like point objects. No, it's and you're looking at this distant galaxy, and here is some object which exerts an influence on light that is coming from this distant galaxy to you. And we found that light actually bends. This mass acts as a gravitational lens which bends the light rays. And what happens is, instead of seeing one galaxy like this, you start seeing two of them. Why two? Because your telescopes can only receive light that's straight, that's arriving at it, the straight path. So this is called gravitational lensing. So you need a very heavy mass. It can be a black hole, which is there in a host galaxy, or a cluster of galaxies, which is lensing light that is coming from something behind it. And when you try to observe it, you can observe multiple objects. Not only do you see multiple objects, just like a lens can enhance the light, sometimes this look actually apparently brighter than what this source inherently is. Okay? So in fact, a lot of research is now going on in observing very distant galaxies using lensing. And this is again one of the things that can only be explained by Einstein's theory of general relativity. Now, Einstein's theory, let us not get into a lot of Einstein's theory. One of the things which is of relevance in this talk is that Einstein's gravity also predicts black holes. Now, what are black holes? Simply, black holes are solutions to Einstein's equation that have very peculiar properties, right, where the curvature goes to infinity and things like that. So here is the center of our galaxy. It is along the direction of Sagittarius A star, and that point is marked as this cross. And what people do is, notice the time over here. This is 1992, and this length scale is 10 light days. These are various stars. These are called S stars. S for sugar, not actually S. S as in sugar. So these are, so for instance, later on we'll have a look at this particular star. It's called S2. But look at what happens. Look at so this is a time-lapse photograph. So these stars are apparently moving. So this is 10 years of observation. Now you zoom in to the center of this. Apparently there is nothing, and yet it affects the motion of the star. Look at this guy. So there is something dark, something massive. You still don't know whether it is massive or not, but trust me, it is massive, which is affecting the motion of these stars, but apparently you can't see it. And it will turn out that this mass of this object is 4 million times the mass of the sun. And yet you can't see it. It seems like a point object which is affecting the motion of this star. All these error bars are basically the measurement of the position of this star. And not only gravitational, general relativity not only predicts black holes, but it also predicts black holes, two black holes which are gravitationally bound to each other to inspiral and merge to generate gravitational waves. I don't know if you can see this trace over here. Can you see this trace? So this is the trace of gravitational waves, and what I'll show you is that when you simulate this on a computer, these two black holes, which are gravitationally bound to each other, we will. So do you see that all the space-time around it is, distorted, and that distortion is traveling out, just like if you throw a pebble in a pond. So imagine that this is a cosmic pond, and you're disturbing it to the motion of these objects. And what it is doing is basically, so I have a running vertical point. I don't think you will be able to see this, but basically it is tracing out this graph. So this is 11 seconds to merger, 5 seconds to merger, and now it has been slowed down so that you can see this. You see that this is these vectors tell you the direction of time. And now these two objects have merged. These two black holes have merged to form a single black hole. And this single black hole is shedding off all its excess hairs. You might have heard about black hole no hair theorems. This is something in action, because any structure to the black hole is quickly shed off in the form of energy, and this energy goes out in the form of gravitational waves. So this is what we want to detect. But before going into that detection, I want to show you that people have been already onto this job. For instance, there is a binary pulsar. Pulsar is a highly magnetic neutron star, which is whose energy is coming to you in the form, it's like somebody is shining a torch at you. This is called this is relativistic beaming, because it's so fast that all the energy is not isotropic, but it is beamed at a particular direction. And what happens is as the two objects come closer and closer, they start spinning faster and faster. So this object was observed from 1975 all the way to 2005. It's still being observed. This blue line is the prediction from general relativity, and these are the observations. And one thing that I should point out is that the error bars have been blown up so that you know that there is an error bar. This is one of the most precise experiments ever done. It is so precise that the error bars will not be seen otherwise. So what we did was you blow up the error bars just to convince people that, look, these are observational data points. And the match is amazing. The match to the predictions of general relativity is amazing. So this is the change in the epoch of periastron. So you fix a point, which is the periastron. Now you know what a periastron is. What is a periastron? You saw the periastron advance of Mercury. You remember what a periastron is? It's the closest point that a pulsar can come to another pulsar. Right? Because imagine one pulsar going around in an orbit. So you try to measure at what time it reaches periastron. So if it's spinning faster and faster, what should happen? The delay between successive periastrons should start decreasing. That's what you're saying. Okay? So this is telling you that the system is spinning faster and faster. And of course, can we see this in one of our detectors? The answer is no. Why? Because we can estimate how long it will take to complete its final inspiral. And that will take 300 million years for this particular system. If some of us are alive until then, maybe we will see it. But I don't have very high hopes for myself. So maybe I hope some of you will eventually see this. But there are other systems for which this lifetime to final inspiral is much, much less. And then we hope to see those. this object. So this is the anyway. Let's not waste time. So for this, it was awarded the Nobel Prize in 1974. So as I said, general relativity predicts black holes to spiral and merge to generate gravitational waves, and this is precisely what we saw a few years ago. So this is the arrow of time. So when you go to the right, it is time is increasing along this direction. So there are these two black holes which are going around each other and then eventually merging, and finally there is a ring down. So once the final object is merges into one final object, it looks very weird. It has a lot of hairs. That means it has a lot of structure. So what it does is that just like a wet dog, it shakes off all the excess moisture, right? The black hole does exactly like that. It shakes off all of that through a process called a ring down. Through a ring down, what it does is it becomes eventually a spherical black hole again, and it loses all that structure through a ring down. And why ring down? Because that ring down waveform looks something like that of a bell. If you take a bell and you hit it hard, the waveform, the sound that comes out of the bell exponentially dies down, but at a single frequency. That's why, by that analogy, it's called ring down waveform. Look at this bottom plot over here. This green thing that you see is the relative velocity of the black holes measured in units of the speed of light, extreme gravity. When it merges, it is almost more than half the speed of light. This object has a mass of 36 solar masses, 36 times the size of the sun, mass of the sun, moving at half the speed of light. I don't think anybody here in this room can actually fathom how energetic this event is. But what I'm trying to say is that as soon as you open this new telescope, which I'm going to show you in a minute, this new telescope is able to see such fantastic objects. I want to see the time. See such fantastic objects which can, which are moving at amazing velocities. And you will see that this also, by very extension, this becomes a laboratory for testing the predictions of general relativity and to see whether this is the ultimate theory of gravity or not. So this is what the prediction was, that we will see such a signal. And this is what we saw on 14 September 2015, when we detected gravitational waves from two black holes that were orbiting each other. And we observed this in the two LIGO detectors. How many of you have heard about LIGO detectors, or just the word LIGO? Oh, that's very nice. So basically, two of the LIGO detectors were in operation. One is in the northwest part of United States, in a place called Hanford, where they have buried all the nuclear waste. And the other one is in the southwest part of United States, called Livingston. And you see that the signal looks pretty much what you expect. This is the signal that you expected to see. Of course, there is noise in the detector. Therefore, you see that in spite of all that noise, this is the signal that we saw. And when you subtract off the signal, this is the residual. It doesn't matter. I mean, I'm not going to get into a discussion about the residuals, but this is a standard analysis that one does when you try to detect a signal. And you can see that these gravitational waves, their frequency increases with time, and that's exactly what you see. When you see a rising frequency with time, so x-axis is time, y-axis is the frequency. So you can see that it gets louder and shriller with time, just like a bird. A bird's chirp, it gets louder. If there are electrical engineers over here, they would know what I'm talking about. It's called a chirp signal, chirping signal. Is there any electrical engineer over here? No? Oh, okay. There's no harm in It's all right. We are with friends. You can tell that you are an electrical engineer. So you know what a chirp signal is, right? Hopefully. Okay, right. So how do you detect such gravitational waves? I mean, in the interest of time, I'll do this very quickly. So essentially, the strongest sources, because space-time is very stiff. It is like a very, very stiff spring. If you put in a lot of energy, it will bend only a little. It turns out that the strongest sources with the strain amplitude will create something like a strain amplitude of 10 to the minus 21. That means if you take a 1 meter ruler, it will change that ruler by 10 to the minus 21 centimeters, whatever. So basically in order to measure these gravitational waves, you have to create a very, very sensitive ruler. And that sensitive ruler should be able to measure distances to 1,000th of a proton's size over a kilometer scale. So that means imagine a ruler that is a kilometer long. I don't know how much is a kilometer from here till IIT Gate maybe. So something like that. And then over that distance, you should be able to measure the change in that length of that ruler to 1,000th of a proton. Now that sounds amazing. And these attempts were happening since 1980s, but the first detection took place only in 2015. Now it took 35 years of no detection, but continuous funding. Some of you will become administrators of DST, and you will be responsible for giving funds to researchers. I want to point this out that it took 35 years of no detection. Every year, the SE you see when you send, you said that, oh, no detection. But please give us $100 million more. And this happened for 35 years. When you become DST administrators, please remember this topic. Okay? That in order to get something of this nature, it takes time, but you have to believe your scientists. So how do you make a detector? The detector basically looks like this. So here is the detector. How many of you have actually seen a Michaelson interferometer? You've seen a Michaelson interferometer. Right? So essentially, this is a Michaelson interferometer, which is very, very sensitive to any changes in distance. Basically, you shine a laser and you split it into two parts, which are at right angles to each other. And let's follow the path of this light beam. It goes into this storage arm. Why do you need a storage arm? Because essentially you want this length to be very, very long. But you play a trick. You place a Fabry-Perot storage arm. What is a Fabry-Perot storage arm? You design this length and the reflectivities of these mirrors in such a way so that it becomes a resonant storage. So light goes back and forth between these arms several times, essentially increasing the length, effective length of this arm. Do the same thing for that side. And then when it comes back, it combines and you get a signal at the photo detector. So if there is a gravitational wave that comes, and if it comes, this is what happens. So this is, so you see that alternatively, this arm will be squished and this one elongated. And in the next half cycle, this arm will be elongated and that arm will be squished by gravitational waves. So obviously there is a change in arm length, which will lead to a change in phase of the light. Somebody wake this guy up. Yeah, stay with us. It won't last very long, I promise. So using this photo detector, you can actually measure it very well. So in fact, I have a nice video for you. So here is this laser which shines light. You have seen that due to gravitational waves, these two arms get alternatively stretched and squeezed. So here is the wavelength picture. It comes back with 180-degree change in phase. And now these two waves will combine and get to this photodetector. If there is a gravitational wave, you will see a change in phase. But of course, as a data analyst and a theorist, it's very easy for me to say it. But of course, this is what has taken 35 years to build such a. When it is out of phase, it creates a dark image. But when it is in phase, it creates a bright image. So by measuring the intensity of light at the photodetector, you can see how much it has changed. But of course, for more bright students over here, you can always ask, if distances are stretched, isn't the wavelength of light that is also stretched? So how can you use it as a ruler to measure changes in length? And for that, I can't see it. There is a beautiful paper in American Journal of Physics. I encourage all of you to just scroll through it. It's a beautiful magazine, which is accessible to students at your level. And it talks about very fundamental things like this. And it doesn't require too much math. But if you are interested, you should read this American Journal of Physics. So here is a picture of one of the laboratories at Livingston. So here is this laser. This building houses the laser, and it is injecting light into the two arms. The two arms are, these are vacuum arms that are 4 kilometers long. That is the end station over here. This is the other one. And then this is where we have the photodetector and so on. So I just want to, before people start getting very antsy, I think I have 5 more minutes. Maybe. So there is a similar detector that is being built in India. If you are from Maharashtra, you probably know a place called Nanded. Is there anybody from, are you from Nanded? Oh, fantastic. So in your backyard, we are building a detector. And when I come there next time, I hope you can join us. So yeah, the excitement suddenly. So in Nanded, a similar detector is being built. It's called LIGO-India. So the civil construction is done, so you can go there for a picnic, for instance. But one of the challenges over there, you'll be amazed at what level things are being built. You know, wind, anything that couples to, see, at the end of the day, this is like an oscillator. Anything that couples to the oscillator is going to add noise to it. For instance, if I have overhead lines, transmission cables, and in India, transmission cables, they send electricity at 50 hertz. So it's like adding noise at 50 hertz. So you'll immediately see a huge spike at 50 hertz. If there is a train, in fact, in LIGO Livingston, very far away, there is a train line. And 11 o'clock in the morning, you'll see a line appear. Because that train, which carries all these logs, it's a heavily wooded area. They cut these trees and make a lot of money out of it. So not the LIGO folks, I mean, the people who own that place. The train, whenever it goes at 11 a.m. in the morning, you will see a line appear in the power spectrum, noise power spectrum. So in Nanded, for instance, one of the challenges that I was talking about is to design buildings to cut down on wind energy. Because there's periodic drafts of wind, and whenever you have periodic drafts of wind, it actually couples to this oscillator, and whenever you have a coupled oscillator, you know that energy transfers from the source to the oscillator. It goes back and forth. One of the engineering challenges, civil engineering challenges, is to build buildings so that it will not, and vegetation, trees, so that it will cut down on this passage of air through it. If anybody is interested in knowing more about it, please, I can help you go to websites where you can find more details. If you want to get involved in it through our summer programs, um, I really encourage you to send me an email. Um, anyway, so I have one last slide for you. This is to discuss how do we know the mass of a black hole? Black holes are there. You can't take a weighing scale over there and wait. Not possible. So how do you do? So the mass of a supermassive black hole can be estimated. So the job of an astronomer is that of a detective. You look at the evidence and then you zoom in on the only possible solution to that problem, right? So for instance, you know Kepler's law. We all study that in +2, maybe, I don't know. +2 mein tha kya, Kepler's law? You had Kepler's law in CBSE, for instance. Right? The square of the time period is proportional to the cube of the semi-major axis. Does anybody remember this? Yeah. And nobody talks about what is that constant? And that constant is devil is hiding, right? This G is the gravitational constant. M is the mass of the black hole, and small m is the mass of the star that is going around. Now, the small m is much, much smaller than capital M. So we will kind of ignore it for now. Let us look at, remember that picture that I showed you near Sagittarius A where things were moving? Let me remind you. So this is a more modern picture of this. Let's follow S2, this yellow one. You remember this picture that we saw earlier? This is S2. Now we are going to use Kepler's law. P square, I can measure the time period of this yellow orbit. I can measure A cube because I know what is the minor, I know exactly what is this ellipse. So of course I can calculate A. The right hand side, everything is a constant apart from the mass of this black hole. I plug everything in and I find the mass of this black hole to be 4 million times that of the sun. But this black hole turns out to be spinning also. We want to know how fast is it spinning. General relativity tells you that for a mass black hole of certain size, they are allowed to spin only up to a certain amount and no more. So how fast is this guy spinning? This is a very hard problem in current astronomy. We can only, indirectly we can measure. See, there is this gas that is falling into the black hole, right? And this gas is getting closer and closer to the event horizon of this black hole, and it's getting hotter and hotter through a physical process known as inverse Compton scattering. And you can look at the spectrum of this emission, and it's not that this black hole is eating the gas all the time. No, if it is the center of our galaxy, this guy is, is a boring fellow. He's not doing anything. Okay. Sometimes, every once in a while, it will eat a little bit of gas and then rest for a long time. Okay. On the other hand, M87, which is the black hole in the center of Andromeda galaxy, is a much more exciting chap. Okay, it's eating a lot. So whenever it decides to eat a little bit, you see that there are these emissions which you can measure in X-rays. X-rays allow you to go very close to the black hole. And by modeling what this profile of X-rays should look like, assuming a certain rotation speed, you can do the inverse problem. I'm teaching a course on inverse problems next semester. That's why I keep mentioning inverse problems. So inverse problem can help you get to the speed of this black hole by looking at this profile. This profile is how much energy at different frequencies of X-rays. Okay. So whenever, anyway, There are other very exciting ways to measure the spin of a black hole. I have one more slide before I end, so relax. There are other very interesting ways of measuring. Just 2 years back, in fact, not even 2 years, 1.5 years back, Abraham Loeb, करके एक scientist है, he figured out that um, whenever a very heavy object spins in general relativity, it drags the space-time with it. And when it drags the space-time with it, it has an effect on how the stars are moving. Remember, the stars are moving. Stars were moving in a certain way, and they were observed for more than 10 years. So if the central black hole is spinning, it's actually dragging the space-time with it. And that will create an effect known as lens-throwing effect. And that effect should be seen in the orbit of these stars. And for our black hole, which is a boring fellow, we don't see any such effect. So they can only put an upper limit on how fast this black hole may be spinning. And it turns out to be just 0.1 of its maximum allowed value. So it's not spinning much at all, to be honest. I'll end this lecture today by talking about what gravitational waves how gravitational effects can help you measure the mass and the spin of black holes. So this is my last slide. So look at gravitational wave signals. So they look like these chirpy signals. So initially, so this is time and this is the amplitude. You see that initially their frequency is less, but with time their frequency starts increasing because the oscillations start happening faster and faster, but also its amplitude also grows. So it becomes louder and shriller. Higher frequency means high pitched sound, shriller. If I plot the same information on a time versus frequency graph, you'll see that its frequency slowly increases, but as it starts merging, its frequency increases very fast. It turns out that there is only a certain combination of masses which will exactly lie on top of what this predicted frequency time graph is. If you take a different combination of masses, this line will go from somewhere else. It will not match the observation. And that's how we know we can put a posterior distribution over the two masses and the spin. For instance, this is the mass ratio and the spin. So gravitational waves already, without even observing electromagnetic spectrum of X-rays that are emitted from gases as they are falling into the black hole, just by observing the gravitational wave signals, you can already estimate the mass and the spin of these black holes. Why is it exciting for a mass to measure mass and spin of a black hole of all things? Because it tells me how these objects were formed. I can work backwards. I can tell, for instance, whether the black holes were formed in a certain way or in another way. It's like the work of a detective. You pick up little clues from here and there, and you try to piece it together until you can, go back way back in time, which you cannot observe, but you can make logical, statements about what must have been happening, and that's how, you, I, everybody here, every object in this room was formed at the end of the day. We are all made up of carbon, nitrogen, oxygen. These were made up of stars. These were made in stars. So with that note, I think I'm right on time. So thanks a lot for your attention and for being here. Thanks a lot.